In this video, we're going to talk about removing nodes from a binary search tree. So down here, you have a typical picture of a binary search tree. And there are three cases to consider when we talk about removal of nodes. The first case, and is the most basic case, is to remove a node which is a leaf. Remember, a leaf is a node that has no children. In this picture, we have 1, 4, 7, and 13. Those are 4 leaves, so those are nodes with no children. So in order to remove a node that is a leaf, means a node that has no children, what we need to do first is obviously to find the node. And it may be that the value that we're given is not present on the binary search tree, therefore there is nothing to be deleted. But if there is a match, then we need to have a reference to that node. So we need to have a reference that points to 1, 4, 7, or 13, which are the 4 leaves in this binary search tree. Also, at the same time that we write the code to do so, we need to keep an external reference to the parent, because in order to remove the node which is a leaf, we need to know where the parent of that node is. And once we have done that, then the process of removal is very simple. We simply take the corresponding child reference that points to the node that we want to delete, and we set it to null. And once we do that, okay, we send that reference to null, then there is no reference that points to the node that we wanted to delete. And remember that Java performs what is known as automatic garbage collection. So let's assume, for example, that we want to delete 7. So we are going to traverse the tree. Okay, we are going to find a match with 7, and there would be a reference to 7, and we have also a reference to the parent node. And once we have that, it's very simple. We know where the parent node is. Okay, we're going to take then the right child in this case, and we're going to set it to null. If we're trying to delete 13, then the same code will take us to 13, so we know where 13 is located because we have external reference to it. We should have an external reference to the parent of 13, which is 14, and then we simply access that node and set the left child in that case to be null, and 13 is gone. So deleting a leaf node from a binary search tree is a very simple operation. So let's go back to the other cases that we have. So the second case will be to delete a node that has exactly 1 child. And it doesn't matter whether it's the left child and the right child. As long as it's only 1, this is what matters. So again, looking at this tree, right, we have 14 has only 1 child that happens to be a left child. 10 has 1 child that happens to be the right child. And those are the only 2 nodes in this tree that has only 1 child. So we're talking in this particular diagram, deleting the node that has value 14, or deleting the node that has value 10. So basically, I'm going to show you now what we do is to bypass the node. In other words, if I want to delete the node that has value 10, then I need to link the parent of that node, which happens to be 8, with the child of that node that happens to be 14. So in a sense, this is like a linear linked list that has 8 followed by 10 followed by 14. And if you remember in the discussion of linked list, to remove that node, we simply bypass that node. Let's assume now that we want to remove 14. So again, this is like a linked list that starts with 10 followed by 14 and ends up with 13. So to delete 14, all we have to do is to bypass the node 14 and connect the node that has 10 with the node that follows 14, which in this case is 13. So we're bypassing 14. So let's go over the rules on a different diagram. The first step, okay, is going to be exactly the same. We need to traverse, and again, this is done probably recursively. We need to traverse the tree until we find the node that we want to delete and its parent. And of course, we're going to have an external reference to the parent. So once we find the node to be deleted, we also know where its parent is. And then the next step is to bypass the node to be deleted. In other words, we're going to take the child reference, and that could be right child or left child, of the parent, and we're going to set it up to be the child reference, and doesn't matter which one it is, right or left, of the node to be deleted. Okay, and as I said, this is very similar to deleting an internal node from an existing linked list. And one more time, remember that once we lose the reference to a node, Java performs an automatic garbage collection. So let's take a look at this diagram. So this is the tree, the binary tree as we have it, and we see here that the only node in this tree that has a child happens to be 60. So we're going to remove 60, and to remove 60 simply means, okay, find the parent, take its child, in this case the right child, and set it to be what? The child of the node that we're deleting. That happens to be the right child of 65. In other words, the right child of 50 should be 65, and that's exactly what we have in here. So basically, we have bypassed 60, and that removes it from the tree. The last case, and is the more complex one, is going to be deleting a node that has 2 children. Okay? So in this case, in this diagram that you have in front of you, we're talking about removing the root. Okay? Well, the root has a right and a left subtree. It has 2 children. Or removing the node that has value 3, or the node that has value 6. Those 3, 8, 3, and 6 happens to have 2 children. So what are we going to do? Okay, so the process to delete a node that has 2 children starts basically with the first step, as usual, okay, which is traverse the binary search tree, trying to find a match and its parent. Okay, so then we need to find what is called the in-order predecessor. So what is an in-order predecessor? Okay, well, first we're going to use this node, the in-order predecessor node, to replace the node that we want to delete. Second, the in-order predecessor is the node that will precede the node that we want to delete if you were to traverse the tree in order. Okay, so think about it. You're going to delete a node. You're going to traverse the tree in order and find the node that comes before the node that you want to delete. This is called the in-order predecessor. Okay, and of course we need to know where it is, so that means finding it, and we need to have a reference to its parent node. Okay, so we have an external reference leading us to the in-order predecessor node. We have an external reference to the parent of the in-order predecessor node. So let me show you what that means in this graph that we have here. Let's assume, for example, that we want to delete the node that has 6. Well, 6 has 2 children. So we're going to traverse the tree, okay, we find 6, and at this point we realize that it has 2 children, 4 and 7. So now we need to write another method to find the in-order predecessor of this node that has 6, okay? And in that case, the in-order predecessor, which is the node that will come before 6 if we traverse the tree in order, is 4. Okay, that's the in-order predecessor, the node that comes before 6 if you traverse the tree in order. Okay, so we need to know where it is. Okay, and now we know, okay, 4 is the in-order predecessor, 6 is the node that we want to delete. Okay, now different case. Let's assume that we want to delete 8, and again 8 is a node that has 2 children. So we need to find the in-order predecessor of 8. The in-order predecessor of 8 happens to be 7. Okay, again, you should traverse the tree in order and make sure you understand that 7 is the node that precedes 8. So now we have a reference to this node, so we know what it is. And of course we know where 8 is, which is the node that we want to delete. Okay, so you will notice after you work on the code for this a couple of things. Okay, the things that you will notice is that the in-order predecessor is the rightmost node of the left subtree. The rightmost node of the left subtree. And again, think about traversing the subtree in order and then realize that the rightmost and the left subtree is the node that goes in order that precedes in order the nodes that you want to delete. So what is the next step? The next step is, first we're going to copy the data of this in order predecessor into the node that we want to delete. So we're replacing the data that we want to delete with the data that we found in order predecessor, all right? And then after we copy that data, then we said, okay, now I need to delete that node which contains the in order predecessor. And in order to delete that node, then we need to apply the rules we just described. It could be that the in order predecessor is a leaf, so we know what to do, or it could be that in order predecessor has one child, and we know exactly what to do. All right? It will be impossible for the in order predecessor to have two children. And that's a good challenge for you. Think about why that cannot be possible. In other words, the in order predecessor is either a leaf or a node that has only one child, but it cannot have two children. Why is that? All right? So let me walk you through graphically so what we do, and let me go back to this diagram. Okay, so this is where we are after we remove 60, and now we are going to remove a node that has two values. In this case, we can remove 40 or we can remove 50. Let's try to remove 50, okay? So again, we find where 50 is. That value is present in the binary search tree. Then we need to find the in order predecessor, and that would be the rightmost of the left subtree. This is the left subtree. This is the rightmost. So we're talking about 45. So the first step is to copy 45 here. So at this point, we have two nodes, this node and this node with value 45. So effectively, we have deleted 50. Now, what do we have to do to finish the process? We have to get rid of the in order predecessor. In other words, we have to delete 45. But to delete 45 is very easy because 45 is a leaf. So simply, we have to take this reference, the right child of 40, and set it to null. And that's exactly what happened. So 45 was copied into the root value and effectively removing 50. And then we deleted the node that has 45 by setting the right child of 40 to null. And that is very simple. Okay? Now, there is an alternative way to replace the node that we want to delete, and that is by using what is called the in order successor. So what is the in order successor? Again, this is the node that if you traverse the binary tree, in order is the node that comes after the node that you want to be deleted. So the in order predecessor is the node that comes before if you traverse in order. The in order successor is the node that comes after if you traverse the tree in order. And likewise, you will realize when you write the code and you execute it a couple of times that the in order successor is found in the right subtree of the node that you want to delete, and is the leftmost node in the right subtree. So remember what we did here. The in order predecessor is in the left subtree and is the rightmost. So here we reverse. The in order successor is in the right subtree and is in the leftmost. It really doesn't matter which choice you make as long as you find the correct in order predecessor or the correct in order successor. Then you copy the value into the node to be deleted, and then you delete the in order predecessor node or the in order successor node.